Imagine you are standing in a kitchen and you've been tasked with making an incredibly complex 100-step recipe.
Oh, God.
Yes, something wildly intricate, like a classic French croquembouche,
All
right?
right. Yeah.
So you're at step 50. You have like multiple pots boiling, sugar caramelizing, and suddenly you just look down at the whisk in your hand and you completely forget what it's for.
Just a total blank.
Exactly. Not only that, but you have zero recollection of what ingredients you even just mixed together in the bowl right in front of you.
Yeah, so you're left staring at, a bowl of white powder and some yellow liquid with absolutely no historical context for how those elements got there.
Right.
Which means predicting what you should do next is, well, it's mathematically impossible.
And that is a fairly accurate representation of what happens to today's large language models when you ask them to execute tasks over a really long period of time.
It really is.
Welcome to the Deep Dive. Our mission today for you, the listener, is to explore this really fascinating, state-of-the-art paper out of Duke University.
Yeah, it's called ProLong. Programmatic memory enables long horizon reasoning.
Right. We are looking at a fundamental weakness in generative AI right now and how a remarkably, counterintuitive approach might actually finally fix it.
Because the problem researchers are tackling here is what we call long horizon tasks.
Right, which are notoriously difficult.
Extremely. I mean, if you want an AI to write a Python script for a single web page, it excels. It's great.
Sure.
But if you ask it to independently explore a novel environment, deduce the underlying rules, and then execute a strategy over, say, thousands of sequential steps, the performance just collapses.
The agent effectively loses the plot.
Exactly.
Okay, let's unpack this. Because I look at models like Claude 3 or Gemini 1.5 Pro, and they have these massive context windows, right?
Oh, they're huge.
Like they can process 1 million or even 2 million tokens. And we see them ace those needle in a haystack benchmarks all the time.
Yeah, where they retrieve a single sentence hidden in a massive document.
Exactly. So why not just rely on better attention mechanisms? I mean, why are they still forgetting what they're doing halfway through a long horizon task?
Well, so the needle in a haystack test evaluates static retrieval.
Okay.
It basically measures whether a model can find a piece of information that remains fixed in a completely static text.
Right. That doesn't change.
Exactly. But a long horizon task is dynamic. We're dealing with sequential decision-making.
Ah, I see.
Yeah, the state of the environment is constantly updating based on the agent's own actions. So in the field, this degradation of performance in these scenarios is known as context rot.
Context rot. Wow, so it's not just a matter of, storage space, it's a structural breakdown.
Precisely. The mathematics of self-attention mechanisms explain why this happens.
How so?
Well, as a context window fills up with a massive trajectory history, every single move, every observation, every minor state change over hundreds of steps, the model's attention gets diluted.
Like it's spread too thin.
Right. The KV cache, which is what stores the key value pairs for all previous tokens, it becomes so enormous that the signal-to-noise ratio drops drastically.
Oh, wow.
Yeah, so the model starts hallucinating connections between irrelevant past events and the current state, simply because the attention mechanism is, spreading probabilities across just too many tokens.
So if the model inherently struggles with these massive, noisy context windows, engineers must be building scaffolding around the models to manage that data flow, right?
They do, yeah.
Yeah.
The industry standard right now is to build complex agent harnesses.
A harness.
Right, a harness acts as a sort of middleware layer between the AI and the environment. It attempts to manage the AI's working memory by using very specific write and read operations.
So it's controlling what goes in and out.
Exactly. They try to optimize what we call the fidelity-tractability trade-off.
Fidelity-tractability trade-off, meaning you have to balance the accuracy of the fidelity, right?
Yep.
With the computational ease of actually retrieving that memory later, which is the tractability.
That's spot on. So to keep the memory tractable, current harnesses use learned heuristics to actively reduce the amount of information they save.
Like compression.
Basically. They'll prompt the AI to write temporary scratchpad notes, or they routinely summarize the past 50 steps into a single paragraph.
Oh, okay.
Or they even compress past events into vector embeddings for semantic search. They're basically trying to mimic human cognitive processes.
But wait, summarizing seems like a really smart, highly efficient way to manage a dynamic environment.
You'd think so, right?
Yeah, I mean, if I sit through a 3-hour strategy meeting, I don't transcribe the entire audio to reference later. I write down 5 bullet points.
Exactly.
Why is that kind of semantic compression failing the AI?
Because what works for human psychology is often a fatal flaw for a machine operating in an unknown, exploratory environment.
Really?
Yeah. Summarization is inherently lossy. When an agent is forced to summarize its past 30 steps, it has to make a judgment call in that exact moment about what is important and what isn't.
Oh, I see. And if it doesn't actually understand the rules of the environment yet, it can't possibly know what's important.
That is the crux of the issue right there.
Wow.
Imagine the agent is exploring a digital grid, right? It sees a blue pixel flash at, say, coordinates 12 by 42 for a single turn.
Okay.
Because the agent is just trying to navigate a maze, it decides the blue pixel is irrelevant noise, so it drops that detail from its summary to save context space.
Makes sense at the time.
Right.
Yeah.
But 50 steps later, turns out that those blue pixels are actually timed switches that open specific doors.
Oh, no.
Yep. And because the agent threw away the coordinate data during the summarization phase, that historical pattern is gone forever.
It's just a race.
Over a long horizon, those tiny, lossy decisions, they just compound into systemic failure.
The agent essentially prunes the branches of its own logic tree before it even knows what the tree looks like.
That is a great way to put it. Which leads us to the prolong framework from the Duke researchers.
Right, the paper we're diving into.
Yes. They looked at this fidelity-tractability trade-off and essentially decided to bypass the semantic limitations of the model entirely.
How?
Well, their approach to the right operation is to not summarize a single thing.
Wait, really? No scratch pads?
No scratch pads.
No vector embeddings, no heuristic pruning?
None of it. The framework is entirely lossless.
That sounds crazy.
It does. Every single observation the agent makes, the exact coordinates of every object, the action it took, the reward score, the error messages, it simply appends all of this raw data into one continuously growing structured text file called logs.txt.
Okay, but isn't that just digital hoarding?
Basically, yeah.
I mean, if it's appending every microscopic detail into a single file, the tractability problem should theoretically be a nightmare.
You would definitely think so.
It sounds like trying to find a specific, I don't know, $4.32 transaction by manually reading through a decade's worth of printed bank statements.
Right.
How is it retrieving anything useful without completely overwhelming the context window?
Well, your analogy of printed bank statements works perfectly if the agent is trying to read the logs semantically, the way a human reads a book.
Okay.
But the secret weapon of pre-roll-long is programmatic memory.
Programmatic memory.
Right. The Duke team designed this harness specifically for frontier coding agents. These models have been heavily pre-trained and fine-tuned on code generation.
Oh, I see where this is going.
Yeah, they natively speak Python, Bash, and standard command line utilities.
So it bypasses the semantic limitations by treating its memory as a literal database.
Exactly.
It's not reading the bank statements, it's writing a SQL query.
It relies entirely on hard code for retrieval. In fact, the pre-roll-long prompt is surprisingly minimal. It's just about 30 lines of instructions.
Only 30 lines.
Yeah. It strips away all the complex instructions about semantic reasoning. It simply tells the agent that it's operating in an environment and that its entire history is being written to logs.txt.
Wow.
So when the agent needs to recall something, it doesn't try to quote-unquote remember it. It uses tools like grep.
Grep. Just these standard command line utility.
Right, for searching plain text datasets for lines that match a regular expression.
Which is incredibly computationally cheap. Like, grep can parse through massive amounts of text in milliseconds.
Exactly. The researchers found that by giving the AI command line tools and a Python interpreter, retrieval remains highly tractable, even for logs exceeding 100,000 lines.
That's wild.
If the agent needs to know every time it moved left and received a negative reward, it just writes a one-line regular expression to filter the log.
And only those specific lines are returned to its active context window.
Exactly.
Okay, the theory is incredibly elegant. Instead of forcing the AI to mimic human note-taking, we just let it operate as a native computational engine, writing exhaustive logs and querying them programmatically.
Right.
But we need to look at how this actually performs, right? Because theory is one thing. The researchers tested this on the ARC-AGI-3 benchmark.
Yes. An ARC-AGI-3 is effectively the ultimate stress test for continual learning and algorithmic reasoning.
Okay, set the scene for us.
It's a suite of virtual games played on 64 by 64 pixel grids, utilizing 16 different colors. But there's a huge catch.
Which is?
The agent is given no rulebook, no semantic labels, and no objectives.
Wow. For you listening, imagine you are dropped into a foreign arcade game, but the screen isn't even showing you pictures.
Right, no context at all.
The agent just sees raw, multidimensional arrays representing the colors. It has a basic action space, move up, down, left, right, click, or undo.
Very basic.
And it has to deduce the fundamental physics of the environment entirely through trial and error.
Exactly. The agent has to interact, observe the state change, hypothesize a rule, and then test that rule.
Right.
A perfect example in the paper is a routing challenge called M000.
M00, right?
Yeah. It's essentially a complex maze environment where the agent must control two separate blocks simultaneously. And the interactions between the blocks and the maze boundaries follow strict but entirely unstated logic.
And out-of-the-box frontier models using standard semantic memory harnesses perform terribly here.
Yeah, completely.
I believe the baseline coding agent they tested scored only, 34.2%?
Yep. The baseline models just get trapped in localized loops.
How does that look?
Well, they move a block, encounter an obstacle, try to route around it, and by the time they get back to the main path, they've literally forgotten the sequence of moves that got them there.
Because of the context rot.
Exactly. The context rot sets in, and they just thrash around randomly.
But with prolong, the agent's behavior fundamentally shifts.
It does. It doesn't just try to memorize the path. Because it has a lossless logs.txt file containing every coordinate change, it actually uses its Python interpreter to build a mathematical simulation of the game.
Wait, really? It simulates the game itself?
Yeah. The logs provide an empirical data set. The prolong agent parsed its history to deduce the exact transition functions of the Manariri's environment.
That's incredible.
And then it wrote a standalone Python script to model those dynamics. Once it had a working simulation of the maze, it executed a breadth-first search algorithm, which is a standard programmatic method for finding the shortest path in a graph over the joint positions of the two blocks.
Wow.
It computed a valid route of over 50 sequential actions and executed them perfectly.
So it got 100%.
It scored 100% on its runs.
It effectively reverse-engineered the physics engine of the game from its own log files, simulated a solution, and then executed it.
Precisely.
That is a massive leap from just guessing based on a scratch pad.
Completely different paradigm.
But the paper details an even more complex environment called G50T, and this is where the orchestration mechanics really fascinated me.
Ah, yes. G50T. The G50T environment introduces a time manipulation mechanic.
Okay, time travel in an arcade game.
Basically.
Yeah.
The agent can take an action that essentially rewinds the game state, but it leaves behind a ghost clone of itself.
Right.
This ghost clone replays the exact path the agent took prior to the rewind. In later levels of this game, the agent has to coordinate multiple ghosts, timing their movements so they hold open specific teleportation switches while the main agent moves through.
The sheer volume of sequential dependencies required to solve that is staggering.
It's massive.
I mean, a move you make on step 10 determines where a ghost will be on step 1 to 50.
Exactly.
And because of this complexity, the agent's lossless memory file ballooned to over 320,000 lines of text.
Which is huge. A standard attention mechanism would just collapse under the weight of 320,000 lines.
Yeah.
The signal-to-noise ratio would be near zero.
Right.
But the programmatic memory thrives on this density. The agent realized that simply using grep wasn't enough to understand the ghost mechanics.
Because it's too complex for a simple text search.
Right, so it independently wrote a sophisticated Python script called regress.py.
What exactly was in that regression script? Like, how did it use it to solve the time loop?
Well, the regress.py script was designed to parse the 320,000-line log and extract the coordinate arrays of every entity at every single timestamp.
Okay.
The agent wrote logic to look for spatial overlaps between its past trajectories and the current ghost trajectories.
Oh, wow.
It used this to verify the exact time-step offset of the rewind mechanic. It was essentially writing automated tests to validate its own hypotheses against a perfect historical record.
It's applying a rigorous scientific method via code.
Yes, exactly.
Formulate a hypothesis about the time delay, write a script to test that hypothesis against the empirical data in the log, and if the output matches the current board state, the rule is confirmed.
That's exactly what it did.
And it scored up to 56.3% on G50T, which is exceptionally high given the density of the state space.
It's incredibly high.
Yeah.
And the implication there is critical for understanding where AI is heading.
How so?
The researchers noted that prolong shows the most significant gains in partially observable environments or environments where the current state does not fully determine the dynamics.
Oh, I see.
If looking at the current board doesn't give you enough information to solve the puzzle, You absolutely must have a reliable, high-fidelity history to deduce the hidden variables.
The performance metrics are undeniable. I mean, across various frontier models, Long scored an average of 18 percentage points higher than baseline coding agents.
Yeah, a huge jump.
But we have to talk about the token economics, because running these models in continuous autonomous loops is computationally expensive.
Very expensive. Cost is the primary bottleneck for deploying autonomous agents in enterprise environments.
Right.
The Duke team compared Prolong to state-of-the-art
Yeah.
specialized agent harnesses, specifically frameworks like Schema and World Modeler.
Okay.
These are highly engineered systems designed specifically to manage long-horizon memory.
And from what I understand, Schema utilizes a very heavy orchestration layer, right?
It does.
It has something like 12 custom tools for memory management, and it uses multiple secondary LLM calls just to evaluate what should be saved, what should be summarized, and how to rank the relevance of past memories.
Yes, the overhead on those systems is massive. World Modeler, for instance, requires a complex 600-line system prompt just to initialize the memory protocols.
600 lines just to start.
Right. And Prolong, as we established, uses about 30 lines.
Wow.
The token economics reflect this architectural difference perfectly. When testing on the Fable 5 model, Prolong achieved a 97.4% score on the benchmark using their best of 2 metric.
Okay, so nearly perfect.
Exactly. And the total token cost for that performance was only $6,750.
And when Schema attempted to reach a similar top-tier result of around 99%, the heavy orchestration drove the token cost up to over $6,447.
Right, almost 4 times the cost. And the disparity is even more pronounced on other models. When running on GPT 5.5, the Prolong framework achieved a 41.2% pass rate while using 5.8 times fewer tokens than the World Modeler harness.
Okay, wait, I need to clarify the mechanics of that efficiency.
Sure.
If Prolong is completely lossless, meaning it is continually appending data and generating text files that reach like 320,000 lines, how is it consuming 5.8 times fewer tokens than a framework that's actively trying to compress and minimize data?
It seems backwards, doesn't it?
It really does.
The answer lies in the tool usage telemetry. The researchers tracked exactly where the computational time, and therefore the token expenditure, was going.
Okay.
The heavy orchestration models suffer from what we can call cognitive thrashing.
Cognitive thrashing, meaning they are spending all their energy just trying to figure out what to think about.
That's exactly it. The data is incredibly revealing. Base agents without Prolong waste, roughly 59% of their computational cycles frantically managing their workspace.
59%.
Yeah, they're constantly calling functions to read notes, realizing the notes are insufficient, calling functions to rewrite the notes, and triggering secondary LLMs to summarize new findings.
That sounds exhausting.
It is computationally exhausting. Because their memory is volatile, they expend the majority of their token budget just trying to stabilize their context window.
They are completely trapped in administrative overhead.
Exactly, but Prolong offloads that entire administrative burden to the local file system.
Because of the log file.
Right. The agent inherently trusts that logs.txt is perfectly capturing reality, so it spends 0 tokens on summarization or note-taking.
0.
0. The breakdown shows it spends 60.6% of its computational time simply writing Python code to solve the core puzzle.
Wow.
And another 9.6% is spent using tools like grep to quickly query the log.
So it drops the workspace management from 59% down to practically nothing, redirecting all of that compute power toward actionable logic.
Exactly.
The agent isn't reading the 320,000 lines back into its context window. It is using command line tools to filter it, meaning only the specific, highly relevant string of text is actually processed as tokens.
Spot on. It completely reverses the token expenditure model. By removing the fear of context rot, the system frees up the agent's contextual bandwidth to focus purely on algorithmic reasoning.
Okay, so what does this all mean for you, the listener, as you look at the trajectory of generative AI?
It's a big shift.
It is. We are rapidly moving toward an ecosystem where AI acts less like a chatbot and more like an independent, asynchronous agent.
Right.
Whether that agent is conducting deep financial market research over a period of weeks, or managing complex software development pipelines, or executing multi-step logistical workflows, we need these systems to be cost-effective, reliable, and capable of holding a narrative thread without losing the plot.
And the main takeaway from the Prolong paper is that forcing an artificial intelligence to mimic human cognitive limitations, like taking bullet point notes or writing subjective summaries, is just computationally wasteful.
Yeah, we've been trying to make them operate like humans sitting at a desk.
Exactly. Leaning into their native architecture is the key. They're computational engines.
Right.
They natively understand regular expressions, data arrays, and Python scripts. By replacing fuzzy, lossy summarization with exhaustive, lossless programmatic memory, we get agents that are profoundly cheaper to run and vastly more capable of deducing complex, long-horizon logic.
It is a total paradigm shift in how we structure agentic frameworks.
It really is.
Yeah.
And there's a specific detail mentioned in the conclusion of the Duke paper that points toward the next logical evolution of this concept.
Oh, the note about co-training the foundation models.
Yes. So currently, Purolong is applied as a harness over existing pre-trained models. But the researchers suggest that future work should focus on co-training models with the harness.
Okay, break that down for us.
This means training a foundational LLM from the ground up, where its internal reward mechanisms are natively intertwined with writing and querying these lossless programmatic logs.
Wow. And for you listening, I really want to leave you with the implications of that future state.
It's pretty wild to think about.
It is, because if AI models evolve past the need for compressed, fuzzy memories and instead maintain perfect, instantly searchable logs of their entire operational existence, what happens when an agent doesn't just run for a 500-move benchmark test, but runs continuously for months or even years?
Yeah, what does that look like?
Right. If an artificial consciousness experiences time not as a fading sequence of summarized events, but as a mathematically perfect database queried in milliseconds via regular expressions, how will that change the way these systems interact with long-term human history?
That is a profound question.
It is something to keep in mind as these architectures mature. Thank you for joining us on this deep dive into the Pro-O-Long framework. Keep questioning the mechanics behind the headlines, and we will catch you next time.